64. Consider the flow sheet in the figure manufacturing C via the reaction A plus B to C. This is my reaction happening or occurring inside a CSTR. CSTR means whatever the concentration here, the same concentration in the outlet flow rate. The split in this is an isothermal CSTR. The split in the separator is perfect so that the recycled stream is free of C and the product stream is pure C. So this is pure C, no A or B, and this is no C. Okay, and this is the recycled stream R. Um, let xi denote the mole fraction of species in the so xp so in the which is operated in excess. Xb over Xa is equal to 4. So the CSTR is operated with an excess of B, and therefore xb over xa is equal to 4. So if this is, for a CSTR, whatever the concentration inside the CSTR, that must be the same as the concentration in the outgoing stream. The rate of reaction is a first order, and it is already given in the CSTR. In the CSTR, negative of RA is equal to, we know that's 1 by V, negative of dNA over dt, and that's equal to KXA, and the value of K is given, which is equal to 5 kilomole per meter cube per hour, which is the same unit, of course, is the reaction rate. So this is the information which are given. The reactor volume is V. So this reactor volume, it has to be optimized with the cost objective function. We'll look into it. So, and it is given as V plus 0.25 R. So if it has to be optimized with respect to V, so we have to find R as a function of V. That's the main objective. So why not we go step by step? Let us take the first step, which we have seen as 1 over V, negative of dNA over dt is equal to KXA. Now, as you can see that this flow rate is 100 kilomole. This is pure C, 100 kilomole per hour. So this is 100 kilomole per hour. That's given. So if C is produced at the rate of 100 kilomole per hour, so A must be consumed at the same rate. That is negative of dNA over dt, which is the rate of consumption of A, must be equal to 100 kilomole per hour. Right? So this is already, we know, 100 kilomole per hour, and this value we know. So we can find out this XA becomes equal to, this is 5, so XA becomes equal to 20 over V. That's one relation. Okay, now the second relation is, we can say in this stream, in the outgoing stream, coming out of the CSTR, XA plus XB plus XC must be equal to 1. All the mole fraction added must be equal to 1. And it's given XB over XA is equal to 4. Therefore, we can say XC is equal to 1 minus 5XA. Very simple. All right. Now, what's the third one? Third one is, if this is, we know, let's call this as an F out. Let's call that coming out of the reactor. So F out. So we can, I'm writing here, F out must be equal to P plus R, where P is the 100 moles of C coming out and R is the recycle stream. So this is being separated here. P 100 moles coming out from here, and the recycle stream is going along this direction. This is my F out coming in. So let's write that down. F out is equal to P plus R. Okay. So we can say R is equal to, see, we are targeting R now because we have to find R in terms of function V, F out minus of P, right? For C balance, if this is my F out, so F out into XC, remember XC is the mole fraction of C here, F out into multiplied by XC, that must be equal to 100 moles of C being produced. I have moles per hour of C being produced, which is going out from here, okay, which is going out from here. So we can say XC, or let's put this as F out is equal to 100 divided by XC. Okay, so let's see what is happening now. What we can do now, F out we got. Okay, so we can write this one as 100 divided by XC, and this one we know equal to 100. Okay, now this XC is equal to, we can say this is equal to 1 minus 5 XA from this relationship here. Okay, and so this R would be equal to 100 divided by XC. Instead of XC, we are putting 1 minus 5 XA. And in terms of XA, we can put this one right here, 20 over V. So we can get R in terms of first XC, and then in terms of XA, and then in terms of V. So if we write down this function here, we get R is equal to 100, if the simplification, R100 by XC minus of 100. Okay. Last stage is easy. We know the cost function J is equal to V plus 0.25 R. So which over XC minus 100. And if you, instead of XC, if you put this one, and instead of XA, if you put this one, this really comes to be equal to V plus 0.25 into 1000, 10,000 divided by V minus 100. Okay. Okay. So if that is so, for finding out the minimum volume, what you have to do, you have to make dj over dv is equal to 0. Of course, for finding out whether that's maximum minimum, you have to take the second derivative. I'm not going into that. And if you put that equal to 0, you will find v optimum is equal to 150 meter cube, which is the answer. And of course, the detailed calculations are shown here.